All right, so let's look at the next part of the notes. One thing I did forget in the part one, here's the rest of that problem. 1.95 times 0.0821, there's our Kelvin. I'm basically just plugging it all into this equation right here, and that gives me my answer. So let's go on from there. So what I want to look at now is gases, mixtures, and partial pressures. So often when we deal with gases, we are looking at a vessel that might have 1, 2, 3, etc. components in it, different gases. All of the things that we looked at before were really dealing with one gas, either going from one state to another or going through stoichiometry from one compound to another. But this is about mixtures of gases at the same time. And when we look at mixtures of gases and their pressures, they are directly proportional to the mole fraction of those gases. So if I have a fraction, it's the fraction of A in moles divided by the total moles, right? And this is important. Remember, we talked about the fact that pressure has to do with the number of collisions per square area or per on the walls of the container, and so you can relate that directly to moles. So the total pressure of any system is the sum of the partial pressures, and it depends on the total moles of gas present, no matter what they are. So let's look at how we're going to use these laws and solve some problems. All right. Okay, so next let's look at exercise 17. So exercise 17 says that we've got this mixture of helium and oxygen. And for a particular dive, we're going to take these two gases and mix them into a container with a volume of 5 liters. So this is going to be my second state, or my V2. And so each gas brings with it its volume, its temperature, and its pressure. So what I want to do is it's asking me what is the partial pressure of each gas in the tank at 25 degrees. So what I'm going to do is I'm going to use P1V1. Notice that my temperature is not changing, and I've got state 1, which is the gas in its original container, and state 2, which is this new tank. So since I have two conditions and my temperature is constant, we're going to use P1V1 equals P2V2. So let's do this for helium first. So if I plug this in, I get 1 atmosphere for helium, 46 liters. Now, what I'm trying to calculate is my P2, and my new container volume is 5 liters. If I solve for all of that, I get P helium is 9.2 atmospheres. Let's do the same thing. P1V1 equals P2V2 for oxygen. That's going to be 1 atmosphere, 12 liters of gas. Let's see, how many sig figs? Just 2. Is equal to P2, this is my new pressure, in this 5-liter vessel. So when I do that, P2 is equal to 2.1. Now remember, based on Dalton's law, P total is going to be PHE plus PO2. So there are my individual pressures, and my total is just 9.2 plus 2.4 equals 11.7 atmospheres. All right, let's look at a little bit about mole fractions. On this next problem, it says the partial pressure of oxygen was observed to be 156 torr in air with a total atmospheric pressure of 743. Calculate the mole fraction of oxygen present, right? So the mole fraction of anything is the mole fraction of that, the moles of that thing over the n of the total. And so when I calculate that, we also know that the mole fraction is equal to the partial pressure of that one divided the pressure of the total. So the partial pressure of this gas, in this case I'm going to put O2 here because now we're going to talk about the specific gas, is equal to the mole fraction of O2 times P total. So if I want the mole fraction, I'm solving for this. So I'm going to rearrange everything. The mole fraction of O2 is going to be equal to the partial pressure of O2 divided by the pressure, the total pressure. And so that is equal to 156 torr divided by 743 torr, which is 0.210. Now, what if I'm given some different data? In this case, I'm given the mole fraction and I want to calculate the partial pressure. So in this case, that would mean the partial pressure of N2 is equal to the mole fraction of N2 times the P total. The P total is 760. The mole fraction is here. This is a super easy one, isn't it? 0.7808 times 760 torr. And so that equals 593 torr. All right, the last problem we're going to do, you did in pre-AP, and that's when we're looking at finding the pressure of a gas, just like we did with PIVMR, gas stoich, except gases can be hard to collect. You can't really just collect them and put them on a scale and weigh their mass, right? You have to find another way of measuring them. And the way that they are measured usually is they are the gas, so this is a reaction, remember, zinc plus hydrochloric acid gives hydrogen gas plus zinc chloride. So when I take the zinc and the acid and I react it, it's going to bubble hydrogen gas, right? So how am I going to contain that and measure it? I'm going to bubble it through water into a container. Now, I can measure the volume if I use, let's say, a graduated cylinder and it has markings on it like this. If I fill this completely with water and let the bubbles displace the water until it comes down, I can actually calculate a volume in milliliters or liters. So this right here is the volume of the gas collected. The problem is that when I do that, I carry with it little bits and pieces of water molecules because they're in there too. There's a little bit of a vapor pressure. So if I want to know the characteristics of the gas only, I have to get rid of the water in the calculation. So let's look at this problem. It says a solid sample of potassium chloride is heated in a test tube. So here in this case, we're heating this. And what's going to happen is it's going to make oxygen gas. And that oxygen gas is going to bubble. And then it's going to displace. And we're going to measure a volume here. Okay? The oxygen was collected by displacement of water at 22 degrees and the total pressure of 754. That means the pressure of the room pushing down here, the total pressure is 754. The volume of the gas collected is 0.65 liters, and the vapor pressure of water at 22 degrees is 21 torr. Now that is a number. This number here is given to you. You actually look it up in a table. So you can run the reaction, then you look it up in the table, and you find out what the vapor pressure is. Calculate the partial pressure of oxygen in the gas sample collected and the mass of the potassium chlorate in the sample that was decomposed. All right, so the first thing I need to do is if I want to calculate how much of this, so I'm going to go from here to here. So the first thing I'm going to do, remember when we do stoich, the best way to get to stoich in an equation is to go N. Once I get N, I can calculate the N of the sample that was decomposed, and I can actually calculate grams if I need to. So what I'm going to do, so in this case I need mass. So ultimately, I need the number of moles of oxygen that were collected, and then I can go here. That's pre-AP academic. The problem is what I collected here is not just oxygen. It's oxygen and water. So what I'm going to do is P total, remember, is equal to the partial pressure of all the components in my mixture. And in this case, oxygen and water. My P total in this case is 754 torr. So what I can do is rearrange this. This means that the partial pressure of oxygen is 754 minus 21 torr. And then when I do that, I get 733 torr. Okay, so now what I want to do is I'm going to calculate how many moles of gas. Remember, that's what we want. We want moles of gas collected. So what I'm going to do is I'm going to calculate my moles. I'm going to use Pivnert to do this. So N is equal to PV over RT. So let's do that. N, so what is my pressure? It says that my pressure of just the oxygen now is 733 torr. My volume is 0.65 liters. My R is going to be 62.6, and my Kelvin is 295. When I do that, I get 2.59 times 10 to the minus 2 mole O2. So let's go ahead and take that. Now I'm ready to do my regular Stoich. So this is Pivnert 1, then Stoich 2. So 2.59 times 10 to the minus 2 mole O2, and I'm just going to go to 3 mole O2 and 2 mole of potassium chlorate. Now I want to go all the way to grams. So 1 mole of potassium chlorate is 122.6 grams of potassium chlorate. So that turns out and gives me 2.12 grams potassium chlorate. So those are my two answers shown there.